Good morning, everyone. This is Gang from Intel SPDK team. I'm from China, Shanghai. So in this talk, I will talk about the QoS that we included in the SPDK 1804 release. So if you would like to have a try on this feature, please just download the latest SPDK release or the upstream code. So here is the agenda that I will talk about the QoS, why we need it. I think it's a basic requirement when we build the shared storage applications in the hyperconvergence case or in the distributed shared case. And the next is talking about the rate limiting on the Bdev internals. And Paul has shared much information on this in yesterday's talk. And next is that we'll also talk about one extension to enable QoS on the vBdev, and we also have a later lab sharing the later morning. And the last part is about some future work. So there still have much work to do, and if anyone would like to join the community, we can to discuss and to share some ideas on this part. So after this summit, I will drive to Intel Folsom campus. So I hope there is not too much traffic on the load, and as shown in this picture, and also there is no noisy neighbor. So for the QoS, actually it is the same that we are trying to solve the basic requirement is to avoid the noisy neighbor. And also that in the case that we are doing some like storage applications, we will always to share something. In this case, we have the shared load, and we want to do the separation. For example, here we have the bus and the taxi only the lane. That's for the fast lane. So in the SPDK, similar that we have the shared resources like the shared network or in the front, and also the shared like back-end devices. So we will also do the similar requirement for QoS. So that's are the two major requirements why we bring the QoS in for the SPDK stack. So here is that, as I mentioned, that yesterday we talked quite a lot about the Bdev layer, and the QoS is implemented upon this layer, and to re-emphasize that it's below the application protocols. So we don't need to care about how the application is talking to the SPDK stack, either through the iSCSI or the NVMe-oF fabric or other protocols, even in the future when we support more protocols. And also it's above the real backend, which means that we can support like different backends like the NVMe SSD or the Optane SSD, and even the persistent memory, and also for the remote connected disks. And in the 1804 release, we have the initial support is to have the IOPS rate limiting. So we'd like to have this feature in the extensible and controllable way. When we talk about the extensible, which means that we can support like the bandwidth control, also for the rate limiting, and maybe for the read and the write separate control. And we have a lot of work to do in the next releases. I will also show a quick introduction on how to use this feature. First, we start the SPDK app target and assign the Bdev to the application. And we have the target here. We have the Bdev. We have a backend device. And we assign it to application. And the application starts IO on the Bdev. And if there is no QoS enabled, the IOs will immediately handle to the backend for the best performance. And if the application needs to have IOPS rate limiting on this Bdev, he can, through the RPC method, to enable it. For example, here we can have the 100K IOPS. So the IOs will come to the Bdev, and some QoS work will be done, and it will only allow 100K IO per second, as described here. And later, if the user wants to change it or to adjust the QoS, he can also, at any time, through the RPC method, to change it. For example, here, just to decrease it to 50K IOPS. Yeah, we have 50K IOPS. It's all done at a runtime, no need to restart the SPDK target. And if later CI is no need to do the rate limiting, just disable it at any time, and the IOs will send down to the backend. So this is a quick introduction on the usage of QoS. And next, I will talk about some internals about how we do it on the Bdev. So it is based on the Bdev core designs. As mentioned yesterday, I just put some keywords here: the IO channel, the Bdev channel, and the Bdev statistics. And next, it is based on the common SPDK concepts, like the asynchronous, the lockless, the polling, and the event-driven SPDK common concepts. And last year, we are trying to have a maybe very clear workflow on how the IOs are handling, and it's also extensible for other QoS policies. If anyone wants to maybe have other implementation, or maybe to have other enhancement on this QoS policy. So let's take a look at one typical usage of SPDK, and to describe the rate limiting workflow. So in this picture, the above is the application stack, and it talks to the middle part is the SPDK stack, and it can through any protocol, for example, through the network protocol, or maybe through the local connected protocol. And for the middle part is the SPDK stack. It's the most important part, including how we translate these protocols and where the block device abstraction layer stays. And here I just use the logical value as previously described and presented by Daniel. And I use the NVMe as the base Bdev. And the bottom is the real devices. So there are 3 layers here. And we have the control paths. One is the conf files that we can configure it when we start the SPDK target. And the other control method is through the RPC core set to enable to adjust or to disable the QoS. And when the application IOs coming through the SPDK Bdev layer. And next we will do the rate limiting here, and then send the device IO to the backend devices. So it's a description on the workflow of this rate limiting. Next is that something about how we do the resource management on this feature. And here I have one IO thread, and the other is the QoS thread. Actually, for the QoS thread, it's just a logical concept. It could be the same is the IOS thread if the SPDK target is configured with only one CPU core. And in the case of more CPU cores are configured, the QoS thread can be the first thread which receive the IOS and start doing the rate limiting. And when the up layer application create an IO channel and associate a vBdev channel and found that the QoS has been configured, or in the case that at runtime receive a request to enable QoS, and the QoS started to do something to for the resource creation. We have the QoS Bdev, and we also need this QoS thread to do the real QoS work on this thread. And meanwhile, we will create and register a QoS poller. The poller is a task running on the reactor to periodically do something for example, the async events, and also can to check the hardware completions. And for once these resources are created, and it can do the IO handling. And later, if the application wants to destroy the IO channel, so in this case, if there is any outstanding IO on the QoS thread, there needs to do the first thing is to clean up those IOs for this IO channel. And when the IOs are cleaned up for that channel, the related information, related resource for that IO channel can be cleaned, and the destroy will be completed. And in the case of that, there is a request to disable the QoS, and all the resource and all the IOs from the IO thread will be cleaned up before the QoS can be safely or cleanly destroyed. And later, when all the resources are destroyed, the QoS resource can be released, and also to unregister the poller. So this is for the resource management on how we fit the QoS related stuff into the vBdev SPDK vBdev stuff. And next is that talk about the normal IO handling. As I said, that we are trying to have a clear or straightforward on how the IOs are handled. For the IO thread, where it receives the IO request, it will just send those IOs to the QoS thread through the message. And the QoS thread will first do, the first thing is to queue those IOs. And later, as said, there is a periodically running poller, and that poller will check. When it wakes up, it will check any allowed IOs to send to the layer below it, to the base vBdevs. And later, when the IOs are completed, it will handle the completion and also send the IO completions back to the originated IO thread. And for the originated IO thread, it will call the IO completion callback, which is set from the upper applications. So in this way, that we can have for the pictures that it's the Formula One, some racing cars, so many years ago, and we can have the higher, medium, low, or corresponding to fast, medium or slow. And we can have the rate limiting for each application on shared backend. So this is the major reason that we bring the QoS on the vBdev and for the shared storage usage case. So I'll talk about next thing is about the one extension that we try to support the per client QoS on shared backend. So this is actually based on the pass-through virtual vBdev, and as mentioned that we have a lab, have some on-hand lab in the later morning, and you can also have some experimental work on this module. And in this case that we already have the QoS on vBdev. I have pictures here. This QoS is on the vBdev, and if we want to share this vBdev to different like applications, for example, here we have 3 VMs. If these 3 VMs want to share the same backend, how we can do it? Yeah, we can leverage the pass-through virtual vBdev. And for each pass-through vBdev, it maps to the same base vBdev. So in this case, that there is an N2-1 mapping. And in our current implementations, and only one pass-through vBdev will have the capability to read and write, and other pass-through vBdevs will only have the read-only capability. And as QoS, as mentioned, it's implemented on the common vBdev, and the vBdev is also a vBdev. So what we're doing on the base vBdev for the QoS, it can also it can also be achieved on the virtual vBdev. So here's that the virtual vBdev, the light blue one, also has the QoS ability. We can set the QoS goal on this virtual pass-through virtual vBdev. And in this way, the VM can see the QoS enabled device. And similar for the second one, and for the last one. So those 3 virtual machines, they actually share the same device on the SPDK target, but they can have different QoS rate limiting. So this means that we can have the QoS on the vBdev, and on the client side, the VM can see the QoS enabled device. So QoS achieved on the SPDK target side, and the client can also see this QoS. So we just offer the QoS control at the target side to achieve the requirement on the IOPS rate limiting. So I will talk about some future work, and in the 1807 release that we would like to do the bandwidth rate limiting, besides the IOPS rate limiting, and also we'll do the read and write separate control, which means the read and write have separate rate limiting on IOPS or on the bandwidth. And next is that consider how to support the IO prioritization for the data and read metadata for the read and write. And the last is that as this feature is developed on the common vBdev layer, so as long as that the SPDK vBdev layer has more functionalities. For example, as mentioned that in the previous talk that CS has some limitations. For example, we so far cannot to expand the different devices. Once the logical volume support the capability to aggregate or to concatenate different backends, the QoS can also be enabled on that logical volume. So this feature can fully together work with the vBdev layer. So as I said, has much work to do. So if you are interested in this, you can join the community. We can discuss and see how how to develop this feature. So here some just to have this again, that we have different channels to join this community. So it's all about the QoS sharing. Any questions?
Yes, I have a few questions. The first one is like the QoS is per client based. So like if I have one, it's like 3 clients, and one shared like a vBdev. Let's say they all have different QoS requirement. If the backend vBdev cannot satisfy all the requirement for 3 clients, is there any like a mechanism for the backend to coordinate this QoS requirements? Is the first question. The second question is like how, because the storage application communicate the vBdev through the storage target, SPDK target, which presents to the application using maybe like say iSCSI long or like a NVMe namespace. So how does client, you have something like out-of-band mechanism to tell about like a QoS to the client, but how does the client associate that like the storage device on front end, like a NVMe namespace or iSCSI long to that vBdev device, because that's a backend which probably is hidden to the client. Also, third question is there any, does like maybe vBdev or SPDK have any mechanism to advertise, okay, some kind of vBdev has QoS control, some not? Yeah, these are my questions.
Many questions. So the first question is that you're asking that if the backend cannot meet the requirement from different clients. For example, like if we have the NVMe, it's about like the Optane, we have 550 IOPS for the reader. So if you mean the case that different clients, when they share the same backend device, like we have 200, 300, 400. Yes, so in this way that in this future, it's actually not possible to achieve the required. It's just to have like the decrease of the goal. So for example, if you know that the device only have like 500, the QoS, the rate limiting should be less than that. For example, 400 or 200. So if in the case that, in your case that it only can achieve as much as it possible, but not possible to meet the requirement. And so far there is maybe no mechanism to do some like balancing or maybe some further enhancement on how to balance each client. It just can do as much as it can for each client. But in this case, maybe not possible to achieve the overall the goal, which is above the hardware's limit. So for the second question is that you're asking how to mapping the front end like devices for the iSCSI long, and about to map it to the SPDK's vBdev. This is the second question.
If we use like a iSCSI protocol, and the front end is iSCSI long, that to the storage application, but the back end is vBdev.
Yeah.
They are not. There must be, if we want to say I have one of the iSCSI long, I want to do some kind of a QoS requirement. I have to, but at the back end, this is advertised as a vBdev has some kind of. There must be some way to let the storage application to know, okay, that device, that iSCSI long is mapped to them, maybe like a vBdev, right? Same thing for NVMe namespace.
Yeah. So we have two ways. One is that we have the configuration file. So inside the file, you can define the lengths, and you can also claim the vbdevs, and the vbdevs can be from the, like as mentioned, from the namespace, or maybe from a malloc. So you have the mapping pre-configured there, and you can also have the QoS. As you have the mapping pre-configured mapping from the long to the vBdev, and later if you want to enable the QoS, so you know your application for the IOs you are doing, so you can just through that mapping to enable the QoS or to adjust the QoS on that vBdev long. So there is some configuration file. Take iSCSI target as example, and similar to other like NVMe-oF fabric target, we have the configuration file to get this mapping. So I forgot the last question.
Yeah, I have two questions as well. So on the workflow slide, you mentioned that you can use the RPC to do query. So what kind of information is exposed about the rate limiting as the query part? Is it just that a limit is set, or do you expose, so if the IO latency is 50 microseconds, part of it could be the device latency versus the rate limiting throttling.
You mean after the QoS enabled?
Yeah, after QoS is enabled.
The latency will be impacted. Is this question?
Yes.
Yes.
So how does the application know if they were hitting the QoS limit, or was the device slow for some other reason?
Okay. So actually we are trying to support the IO state 2, and that 2 can try to get it's also talking to the SPDK, and it can get the IO statistics in the real time for the vBdevs. So once we have the QoS enabled, and you can use the IO state 2 to correlate the SPDK target to get the real IO statistics. For example, like we set the 100K IOPS, you can see whether it's 100 IOPS. And also, I think like the tool, like the FIO, it has some real-time display on how when we are doing some testing, how the IOPS, yes.
Okay. Yeah, so that should be good. Second question. So if the application is, so let's say you've set the QoS IOPS limit to 100K, but the application is running at about 50K IOPS steady. Because of this QoS model, when it's enabled with the message passing between the IO thread and the QoS thread, what's the overhead to the latency when the application is not actually hitting the QoS limit, but QoS is enabled?
Yeah, this is a good question. Actually, we are doing some testing just recently, maybe in the past 2 or 3 weeks. We are evaluating how our SPDK, like the async or the event-driven, this framework bring the overhead. So far, there is some overhead there, but we are further doing some testing to confirm this overhead. I can say that there is overhead here. Yeah.
And I just want to clarify, the QoS thread is actually not a dedicated thread. It's dynamic. It's the first thread on which you send an IO. So if you're doing all of your IO from just one thread, the QoS thread is your thread. It's the same one. So there's much less overhead. It's only if you do additional IO from other threads so they get evented to the first one. And then if you close all you close down the vBdev and you reopen it up later, it'll move.
So any other questions?
Yeah, we got one over here. Oh, yeah, one over here. Okay.
So it's more of an implementation question, and it's kind of what he was talking about, right? That the QoS thread is the one that's polling for all the new IO commands, if I understand, once the QoS is configured. And once it has hit the rate, is the IO returned back to the user saying that, yes, you have hit the limit, or it's queued internally? That's one part of the question. And are the resources, so in case the rate limit is already reached, does it mean the resources have already been acquired and have to be freed, or the resources, the buffers and things like that for the read and write operation, or are they acquired only if the I/O is allowed to proceed?
So the first question is to, it will, for the completion, it will just.
So the first question is about the QoS thread, right? And
yeah,
I am
QoS
guessing, I have not seen the implementation of it yet.
Yeah.
I'm guessing the QoS thread is the one that's actually polling for the new I/O commands and actually processing the I/O. It's
Yeah.
there is no context switch between an I/O channel and the QoS channel.
Yeah.
Is that an accurate statement?
Sorry, I didn't catch your question. So what's the question? You mean context switch from the I/O channel or from the?
From the I think Ben kind of answered the question in a way.
So I'm sorry. Your question is the thread that submits the I/O, and then you have the thread that actually is doing the QoS. Like, is there a context switch between
Yes.
the two? No. So basically, the thread that submits the I/O uses the message passing. So it'll send a message to the other thread. It's just another, it's sending the message to another reactor.
Okay.
And it'll go down to that.
And if it hits the rate, for example, there's already enough I/O that this I/O has to be failed.
It'll get queued on the QoS thread, not on the thread that submitted it.
Okay.
Yeah.
All right. Okay. I need to look into the implementation.
Okay.
Okay, thank you. Okay, thank you all.
We have one more. We have one more question.
Okay.
So if you want to carve the bandwidth out, for example, like if you have lots of different apps, and then storage apps tend to be bursty. So if you want to guarantee the the rate limiting, then you sort of have to be very conservative and then just carve out all the rate properly. So it'll be wasting lots of bandwidth. Is that something you deal with it? For example, like, can you do it more like priority rather than just fixed IOPS? Because I mean, it's really hard to calibrate a device IOPS, right? I mean, for different read and write, for different IO size, for different Q depths, the IOPS could be, it's not a fixed number for a particular block device.
So I think your question's actually a much broader conversation. So that's probably something that we can try and tackle here, and during a break or something.
Yeah. Okay.
Thanks, Gon.
Okay. Thank you.